All right. Section 2.5 is infinite limits. And like I just said to Rachel, sometimes limits don't exist because the y values are going to infinity or negative infinity. And up until now, we have just written does not exist. We're going to change our notation just a little bit here and use some notation that tells us how the limit fails to exist. Before we get there, this was in section 2.4, we talked about 3 different scenarios, not 2.4, this was 2.2. We talked about 3 scenarios when we would say the limit of the function as x approaches 0 does not exist. Can you think of what those 3 scenarios were? Or any one of them? Tell me one.
The x and the left side and the right side of it approach 2 different numbers.
Okay, that's perfect. So coming at 0 from the left, we just got a different y value than coming at 0 from the right. Left hand limit exists, the right hand limit exists, but those 2 values are not the same, and therefore the 2-sided limit doesn't exist. What somebody else give me a scenario when we've said the limit doesn't exist. What do you think, Rachel?
When it takes off, the inverse takes off towards infinity or negative infinity.
Okay. Okay, sounds good. What about if we have a vertical asymptote and we have a graph that approaches either infinity or negative infinity, or maybe it approaches infinity from one side and negative infinity to the other. Can you think of that third really weird situation where we said the limit didn't exist?
It's been an oscillating function, like
You even remembered the word. Also, oscillating function was the one that looked like at the EKG of somebody having a heart attack. When the graph gets close to 0, the graph's just zigzagging so fast that the limit doesn't exist. Now, which of those graphs have a discontinuity? You know what? I don't know why I scooted over and put a discontinuity at maybe 1 or 2, because we were supposed to be doing the limit as x approaches 0. Supposed to be as x approaches 0. So that should have been approaching my y-axis. Of that. So which of those 3 graphs illustrate a discontinuity at 0? First and second. The third's not discontinuous at 0. The limit just doesn't exist as x approaches 0. So I'm going to put on this last one, continuous at x equals 0. And the other 2 are discontinuous at x equals 0. If I label these, just to make them easier to talk about, if I label those 3 scenarios, A, B, and C. How did it get different than what mine printed? I have no idea. Okay. Which of the graphs illustrate a discontinuity at 0? You told me that A and B do. And are those discontinuities removable or non-removable?
None.
They're both non-removable. They can't be fixed just by filling in that circle or, well, no way to fix the vertical asymptote. So they're both non-removable. Think about it. You have to draw a picture to think about it. But if you have a horizontal asymptote and a graph, let's say at -4, you have a graph that looks like this. You can still find the limit as x approaches -4. It's whatever that point is. It's a y value, so the horizontal asymptote doesn't affect what the y is approaching as x approaches that constant. Now, way later in another section, we're going to define a horizontal asymptote is a limit as x gets closer or as x goes to -infinity or positive infinity. That's what causes a horizontal asymptote. Your x's are approaching some limit. No, I'm sorry, your y's are approaching some limit as x goes to either -infinity or positive infinity.
Just where the.
Yeah, for now, yes. How did I have something different than you?
We'll do it.
Okay. No, I printed it from my computer instead of Momentum, and therefore, I have something on my computer I forgot to upload to Momentum or something. So the D part, yours says describe and illustrate a scenario where the function is discontinuous at 0, but the limit still exists. Is that on all of your papers?
Yes. Yeah.
Not on yours?
So.
But you printed from Momentum.
Yep.
How the heck? When did you print from Momentum? Okay, that's what it is. I uploaded a new one yesterday, but I wanted to have that. Okay, I don't know. I'm gonna write it in here for you then, Richard. Describe. And illustrate a scenario.
The spirit is here.
Hmm?
Spirit. Yeah.
Yay, the spirit of Abigail.
Spirit of Abigail.
Hey, y'all, while I'm writing this, would you pass this paper over to Abigail, please? Illustrate a scenario where f of x is US at x equals 0, but the limit as x approaches 0 of the function exists. Now, all of y'all have that typed very pretty, except for Richard. Richard's got to copy down my scribbling here. But we did have room for a scenario. What would that look like? That is discontinuous at 0, but the limit still exists. How can that be, Madison? There can be a hole in the graph at 0. So maybe it's that line. And then we can say there's a discontinuity not only in our graphs A and B, but also C. I do mean D. Stop this recording right now. Yes, I'll also mean D. The discontinuities in A and B are non-removable, can't be fixed just by filling in a dot. And the discontinuity at D is what? Removable, because it could be fixed just by filling in the dot or redefining the function at 0. All right, so today we're looking at functions again, and we're identifying discontinuities. And we're determining whether those discontinuities are removable or non-removable, and what it looks like on a graph when a discontinuity is removable versus non-removable. I've got 3 more examples on here, and then we'll look at some in the book. What can you tell me about the function value and the graph of the function at the indicated values of x? So A is a rational function. And we want to talk about what that function, what's going on with that function at +2 and -2. Tell me how you'd figure that out. All right, can you, put 2 or -2 into that function?
Good, but it wouldn't give you.
It would give you undefined. Yeah, you could, but it would blow up. So the function's not defined at 2 or -2. F of 2 and f of -2 are undefined. That's one thing that we could say. Undefined would mean either there's a hole in the graph or some big hop, skip, or jump in the graph. Something is going on at 2 and -2 that makes that function undefined. So how can we talk about specifically whether or not the limit exists at, let's say, x equals +2? You should. You always should start with a rational expression by factoring it and seeing if it'll reduce. You can factor a 5 out of the numerator. The denominator is the difference of 2 squares. And you can divide out the common factor as long as you say this expression is equivalent to that expression at all except for one number. For what one number are these two expressions not equivalent? -2. I can put -2 into the second expression, but I can't put -2 into the original expression. So I really can't say they're equivalent. I can say they're equivalent for all values except -2. Now, what does that mean is going on with the graph at -2? Yep. Hole in the graph at x equals -2. Hole in the graph always comes from the common factor that you cancel. So that's all we can say about the graph at -2. There's a hole in the graph. What about +2? Because we can't do anything about that discontinuity. We cannot let x be +2 even in the reduced function. So we can say a vertical asymptote at x equals +2. And you can graph that on your calculator and see those two things. It's hard to zoom in enough to see a hole in the graph. That's why it's so important that you be able to identify that hole in the graph algebraically. It's pretty easy to see the vertical asymptote. The graph your calculator can't graph a vertical asymptote because a vertical asymptote is not a function. It fails the vertical line test because it is a vertical line. But you can tell that your x's are getting infinitely big or infinitely small at 2. And that's actually what the definition of vertical asymptote is. Vertical asymptote is the line, the vertical line, which at x equals some value, your y's are either going to +infinity or -infinity, or possibly +infinity on one side, -infinity on the other. That's the definition of what it means to be a vertical asymptote. Madison, did you want to say something? Oh, yeah, we got a bumpy floor, I think. All right, so that's all I need to say about this first example. What about the second one? Think of the graph of natural log or the domain of that expression. How about that? Tell me the domain of that function. Anything greater than 3?
3.
Three included, what about 2.5?
So, okay, everything greater than 2.
Oh, everything
Not-
greater than 2, not including 2, because I can't take the natural log of 0. So the domain is all the x's that are greater than 2. And so what can you tell me about this graph at -2?
It's
Yeah, it's just undefined. There is no graph to the left of 2.
Sorry, what is it now, guys?
Yes, undefined can be just a hole in the graph, but you can look at the graph on both sides, like on the A part here, we would say that the function's undefined at -2, but the limit still exists. You can approach -2 from either side. In this B part, you can't even approach -2. There's no graph anywhere to the left of +2 for that function. All right, what can we say about the graph at x equals 2? The function's also undefined. Is there anything going on? There's nothing going on at -2. But is there anything going on at +2? There's a vertical asymptote. Remember the graph of a logarithmic function has a vertical asymptote at whatever makes the argument 0. And then the graph is basically that shape. So that one is the basic shape of natural log, but the whole graph is shifted 2 to the right. So there's a vertical asymptote at x equals +2. All right, what about part C? F of x equals tangent x at x equals multiples of pi/2. It's tangent's undefined at pi/2.
So
Is it undefined at all the multiples of pi/2?
not.
The odd half pi is where you have what on the graph of. All right, so f of x has vertical asymptote at, how do you write odd half pi's? Pi/2 times any odd number, and you can get any odd number by doubling an integer and then adding 1. So that's the odd half pi. And what about the even half pi's? That would always give me an even number, or I could just say pi times n.
Oh, yeah.
All right, that would give me the same thing. F of x has, what's going on at the whole pi's, the tangent?
It's at like 0.
You've got x-intercept. At the whole pi. we just know what the graph of tangent looks like. It looks like x cubed between its asymptotes. The definition of vertical asymptote is if there's a C value, which at that C value, the y's are either going to positive infinity or negative infinity. That's the definition of vertical asymptote. All right. That definition, these are called infinite limits when you want to say that my y's are going to infinity or negative infinity. So far, we've just said the limit doesn't exist. Saying a limit equals infinity or negative infinity is not saying that the limit exists. It's saying specifically how the limit fails to exist. And that's the caution at the bottom of page 107. When you write limit as x goes to c of f of x equals infinity, I could just say plus or minus infinity and I wouldn't have to write it again. That means the limit does not exist and this is how the limit fails to exist. You write a limit equals infinity. That does not mean the limit exists. Now we have x is going to, y is going to infinity or negative infinity. Rather than writing does not exist, we're gonna write positive infinity or negative infinity. Now, is there still a situation where a limit doesn't exist, but you could not write infinity or negative infinity?
See,
Yeah, this one, the limit exists, but you could not, this one, the limit fails to exist, but it's not because there's a vertical asymptote. It's not because your y's are going to infinity or negative infinity. What's that one other note I wrote? If a rational function, now remember the definition of a rational function is a quotient of two polynomials. So if you have the quotient of two polynomials and there is a non-removable discontinuity at C, that means there's still a factor in the denominator that you can set equal, that you can find what makes it 0. And there's nothing you can do about it, it won't cancel out. Then the function has a vertical asymptote at C, and the limit as x approaches C from the left or from the right is either positive infinity or negative infinity. What we're going to write instead of does not exist. If C is a removable discontinuity, there is no vertical asymptote at C. There's just a hole in the graph at C. So let's see what tonight's homework is going to look like. Does everybody have the copy I made of 2.5 homework? Oh, okay. And you can just write on this for your homework, just like you did last night. Most of these, we're going to determine whether the graph is going to positive infinity or negative infinity by looking at the graph on the calculator. So 17 through 32. They find the vertical asymptotes, if any, of the graph. Does number 18 have any vertical asymptote? No, why?
because you can't get a negative out of a square unless you do an imaginary number.
Yeah, and we're only talking about real numbers here. So I'm gonna say t squared plus 1 does not equal 0 for any real number. So there are no vertical asymptotes. What about number 20? Could it possibly have a vertical asymptote? Oh, that denominator is a good old sum of two cubes. Do you remember what, the factorization of sum of two cubes looks like?
The first one is x plus 5, and then is it the first term squared, opposite sign, then final has to be a plus, and then it's the last.
So it's a
And the
binomial
backwards
times a trinomial. You get two terms times three terms. So I'm gonna put down parentheses for that. And then try to remember the words that help me factor the sum of two cubes. It's cube root of the first term. Same sign. Cube root of the last term. And then you look at that binomial factor and you square the first term. Take the opposite sign. Multiply the two terms. Last sign's always positive, and then you square the last term. Now, will that factor any further, that trinomial?
No.
No, it looks like it could be a perfect square trinomial, but in order to be a perfect square trinomial, this would have to be a 10x in the middle. So, 8, that just happens to be the same thing in the numerator. X squared minus 5x plus 25. So you can cancel out the common factor there and say that that just equals 1 over x plus 5. Now the exception would be what made this 0, and if you use the quadratic formula to find what makes that equal 0, you would find real quickly that only imaginary numbers make this 0. So I don't have to list these two are equivalent except for when x equals something, because we're not talking about imaginary numbers anyway.
There's no holes. If they're all right.
Right, so there are no holes in the graph, but what? There is a vertical asymptote at, right, vertical asymptote at x equals -5. A non-removable discontinuity in a rational function. Are you realizing how many words you've learned? Like that sentence made sense, hopefully. There,
Hopefully.
there's a vertical asymptote at x equals -5 for this fractional function because it's a non-removable discontinuity at -5. All right, 22 is basically the same thing. I'm not gonna do it. You'd have to factor it by grouping. What about 24? Oh, it's so innocent with, but it's got that,
-2x, and we go
yeah.
like 1 x over 1 over e.
But e can't be 0, so
Yeah. Even 2.
It does help me to think of it as, hey, that is a fraction. But then like Madison's saying, yeah, it's a fraction, but there's nothing that makes, there's no power of e that gives you 0. So what does that tell you? No vertical asymptotes. Remember what the question is. The question's asking us for vertical asymptotes. And there's not one. You want to put a little because there, it's because e to the 2x doesn't equal 0 for any value of x. What about 26?
Where it equals 0 is the vertical.
Okay, vertical asymptotes at what makes the argument 0. What makes the argument 0? Plus or minus 2. Can you let, on that one, can you let x be 3 in this function? Yeah, can you let x be -3?
Mhm.
Yeah, can you let x be 1? So where would this function not have any graph at all?
Two.
What are you saying, Richard? Well, it has vertical asymptotes at 2 and -2. I'm asking where is there no graph at all? In between those vertical asymptotes, it only has graph outside its vertical asymptotes. 28 is easy if you can do 26. What about 30? Where would tangent pi x have vertical asymptotes? What does that pi change about the function as compared to just tangent x? What's different when you graph tangent pi x? Okay, I heard, couldn't see whose lips were moving. Abigail and you spoke. Well said. That's changing the period of the function. So we would say normally tangent has its asymptote where? Normally at the odd half pi's. So instead of saying x is an odd half pi, we're gonna say pi x is an odd half pi. And so what would that mean? X equal.
Times 2.
If you divide both sides by pi, you just get 1/2 times 2n plus 1, which is just the odd half, not the odd pi's, because it already has the pi in it. This is one way to write that answer. That's where vertical asymptotes are. If you look in the back of the book and it's not written like this, if they happen to have just n plus 1/2, how could you tell if your answer was equivalent to theirs? Or how could you tell if your answer was right? Or yeah, just look at it and go, are these two things the same thing? Yeah, if I distribute the 1/2, that's what I get. So maybe that's simpler. Any whole number plus 1/2 would give you.
That'd be vertical asymptote.
So I can say vertical asymptotes have either one of these two things. All right, what about 32? G of theta is tangent theta over theta. What are our worrisome values of theta? 0 would be a problem because that would give us 0 in the denominator. What else would be a problem?
Odd half.
The odd half pi's. Let me write it this way. The possible vertical asymptotes at x equals 0 and x equals odd half pi's. Now, odd half pi's definitely are a problem. There's nothing I can do about it because tangent has vertical asymptotes there. What about at x equals 0? Well, I'm tempted to say that I know I can't just let x be 0, but can I let x get close to 0? That makes me think back to the limit.
The bound.
One of my special limits is as x approaches 0. Is there any way that I could split that function into something that would give me one of my special limits? I could write it as sine theta over theta times 1 over cosine theta. That's what I think. But I want to double check it. Does that really multiply back together to give me the same thing as my g of theta is? Well, I'd have my sine over cosine, that is tangent, and I have my theta in the denominator. So yeah,
Yeah.
they're the same thing. Does this limit exist? Well, this part of the limit is what? 1. And what about this? The limit as x approaches 0 of cosine theta. That's also 1. Cosine's your x value, and at 0 radians, your x value is 1. So that limit exists. How can a limit exist when the function itself doesn't exist? That's a hole in the graph. I know it. Honestly, if I hadn't been doing this 30 years, I would have looked up and said, oh, obviously, you can't let it be 0, so there's a vertical asymptote there. That's not correct. If the limit exists, even though the function doesn't, and if the direction said, so where are their vertical asymptotes? Then the only answer is at the odd top. Ms. Rachel, what were you wanting to ask?
I was wondering why we assume that x one of the get 0 in the denominator instead of vertical.
Not always, but a lot of the times, like here we knew that there's a vertical asymptote at -5 because we can't cancel out that factor. But on another problem where we could cancel, then we get hole in the ground.
If you just have x in the denominator, is that a vertical asymptote?
It depends on whether or not you have an x you can cancel with it in the numerator. For example, if I had the limit as something x, let's say x goes to 0 of x cubed minus 9x over x, would there be a hole in the graph or vertical asymptote at 0? Because 1, you can factor an x out of the numerator, cancel your common factor, and say that this is equivalent to just x squared minus 9 for all values other than 0. And since you canceled out that 0, it's not a vertical asymptote at 0, it's a hole in the graph at 0.
But it's good.
Then it would be a vertical asymptote. Because that's the note that I have for you right here. A rational function has to be an algebraic function, quotient of 2 polynomials. If you have a non-removable discontinuity, you have a vertical asymptote. If you have a removable discontinuity, you have a hole. All right. 34 through the rest of the homework. And for some reason, I don't have number 53 and number 55 on here. The homework, I didn't mean 55. The homework goes to 53, so y'all have to copy that one out of the book. For the ones that you can tell there's a non-removable discontinuity, just look at the graph to tell whether the y's are going to infinity or negative infinity. Number 33 to 36 say determine whether the graph has a vertical asymptote or a removable discontinuity at -1. What do you think about number 34?
Yeah.
What are you saying, Isaiah? Because why?
It's all right.
That's exactly right.
Yes.
X minus 4 times X plus 2. If you cannot remove that factor, then you have a non-removable discontinuity of a rational function. And what is indicated by a non-removable discontinuity for a rational function? Vertical asymptote. What about 36? Vertical asymptote or removable discontinuity at -1?
Cause I don't see a way to get that x squared plus b.
Yeah, there's nothing you can do about that. You just have -1 makes the denominator 0. It's not fixable, so there's a vertical asymptote at -1. In your homework, you can see that 33, there's just going to be a hole in the graph, a removable discontinuity for 33. And then 37 through 50. Oh, I do have 53 and 54 up there. Okay. I don't have to go back and fix anything on this handout. Find the one-sided limit if it exists. So number 38. How can you find out whether the limit as x approaches 2 from the left exists?
Direct substitution.
You try direct substitution, because if you can find the two-sided limit by direct substitution, then both one-sided limits exist and are whatever you get when you substitute 2 directly into that function. You put in a 2, you get 4 over 4 plus 4, or 4/8, or a half, or yeah. A little bit harder to factor. Yeah, I don't want to do that. It just takes a few minutes more to factor. What about 42? Can you find that limit by direct substitution?
No.
No. Do any of your tools for resolving indeterminate form allow you to get an expression where you could plug 0 in? Simplify complex fraction? Okay. I love that you can rattle those off. That's important. But if there's no way to fix that expression so that I can plug in a 0, that tells me there's a non-removable discontinuity at 0. What does that mean occurs on the graph at x equals 0? The vertical asymptote, and my y's are either going to be going to positive infinity or negative infinity. So what I'm going to do on the homework, I'm not going to write does not exist. Now that we've talked about infinite limits, I'm going to say 6 minus 1 over x cubed. Graph it. And sure enough, I can see that there's a vertical asymptote at 0. I'm just going to look back at the problem to see which one-sided limit it's asking for. It's asking as x approaches 0 from the right. Here's x equals 0. As this graph approaches 0 from the right, what will you write for that infinite limit?
Negative.
Your y's are going to negative infinity. And does that mean you have found the limit? No, the limit doesn't exist. You just told me how the limit doesn't exist. 44 will be pretty much like that. There's nothing I can do to resolve that indeterminate form. So I know there's a vertical asymptote. I'm just going to look at the graph to see whether the y's are going to positive infinity or negative infinity. What about 46? The limit as x goes to pi over 2 from the right of -2 over cosine x. How could I tell if that right-hand limit exists? Try direct substitution. Could I let x be pi over 2 in that expression? Cosine pi over 2 is 0 and -2 over 0 is undefined. So, is there anything that I could do to resolve that indeterminate form? The only special limit that has cosine in it is 1 minus cosine x over x. I better memorize my special, that special limit I forget sometimes, but I'm gonna make sure I have that one in my head before Tuesday. I think it's 1 minus cosine x over x. And there's no way to manipulate that into that expression. So, that means there's a vertical asymptote as x approaches pi over 2 from the right. I'm just going to graph it and see whether the y's are going to positive infinity or negative infinity. -2 over cosine x. Make sure your calculator's always in radian mode for calculus. -2 over cosine x. Graph it. I could either change my tick marks to make them count by pi over 2s, or I could say, what number is pi over 2 close to? As a decimal. It's about 1.5. It's 3.14 divided by 2. It's about 1.5. So as I'm approaching 1.5, that's about right here. And I want to be approaching that 1.5 from the right. So here's my vertical asymptote. I'm approaching it from the right. What will you say about that limit? My y's are going to positive infinity.
So even if we're doing three, we need to be.
If you're not doing trig, it doesn't matter what you're in, because degrees and radians don't affect anything but trig. It's when you're doing trig that it must be in radians. Otherwise, it doesn't matter. All right. Basically, that's what you do on the rest of the homework. You just try direct substitution. If you get indeterminate form and you cannot resolve it, that tells you there's a vertical asymptote, and you look at the graph to see whether the y's are going to positive infinity or negative infinity. And this is where the Miles law of calculus comes from. 41 to 54. I wrote down the answers. Yeah. They're all either positive infinity, negative infinity, or 0. 41 through 54. Yeah. All right. So, you understand what you need to do tonight? And most importantly, if you have not finished that practice test, A, you're a knucklehead because the test is upon you. B, you can only ask me questions tomorrow about problems you've tried. Tomorrow's our review day. So don't ask me a question on a problem you haven't even attempted or looked in your notes to try to remember how we did that. But if you've attempted a problem and could not get the right answer, then by all means ask, and we'll do all we can do of those in an hour. And then Madison's study group is tomorrow 4 to 6. All right, let me stop this recording, and then if you have any questions, ask me.